Welcome to This Explainer. Today, we're diving into a genuinely fascinating thread of engineering that literally weaves through over a century of history. We're going to explore how the fundamental physics of rotation, specifically the gyroscope, doesn't just have the potential to stabilize our future transit networks, but could actually unlock massive, clean energy grids hidden deep within the Earth. So let's kick things off with a question that sounds kind of impossible. How on earth does a forgotten, century-old single-rail train connect to the cutting-edge, next-generation geothermal power that might just save our planet? I know, it sounds like straight-up science fiction, but trust me, the connection is incredibly real. The whole answer lies entirely in the physics of the gyroscope. Now, at its core, a gyroscope is just a spinning rotor. But when it spins fast enough, it generates this immense angular momentum that fundamentally resists tipping over. Think about riding a bicycle, right? It's really hard to balance when you're completely still, but once those wheels are spinning rapidly, they actively want to stay upright. If you try to push a spinning gyroscope over, it reacts by moving at a right angle to your push. It's a quirky little phenomenon known as precession. And this invisible stabilizing torque, that is the magical force connecting absolutely everything we're going to discuss today.
Here is our roadmap for today's explainer. First, the magic of hurrying precession. Then we'll look at carbon fiber and magnetic bearings, followed by the hybrid transit ecosystem. After that, deep earth geothermal power. And we'll wrap up with drilling with gyrotron beams.
All right, section 1, the magic of hurrying precession. Our story actually begins with an Irish-Australian engineer named Louis Brennan. Between 1903 and 1910, Brennan rapidly developed a totally mind-bending invention, a gyroscopic monorail. By 1910, at the White City exhibition in London, get this, he was carrying up to 50 passengers, including Winston Churchill, on a massive 40-foot, 22-ton train that balanced flawlessly on a single, narrow rail. And the wildest part? It maintained perfect balance even when completely stopped. Just imagine that, a huge steel vehicle loaded with people balancing perfectly on a wire-thin rail without even moving.
Now, Brennan faced a huge mechanical challenge. You see, a single gyroscope will keep a train upright on a straight track just fine. But as soon as that train tries to take a corner, the gyroscope resists the turn, which would cause the train to violently capsize. So Brennan came up with a brilliant solution. He used two massive 0.75-ton counter-rotating gyroscopes. By linking them with gears so they spun in opposite directions, they completely canceled out the unwanted torque during turns. It's this elegant mechanical dance that allowed the massive train to gracefully lean into corners, kind of like a motorcycle rider leaning into a sharp bend. So you might be wondering, how did the train actually correct its balance when, say, a heavy load shifted from one side to the other? Well, Brennan utilized a principle called hurrying precession. When the train started to tip, a pneumatic actuator system would actively push against the gyroscope's natural wobble. This active hurrying literally tricked the physics. By forcing the wobble to speed up, it generated a massive counter-torque. It essentially pushed back against gravity and miraculously forced that 22-ton train to stand completely upright. We're talking about active stabilization decades ahead of its time. Moving on to section 2, carbon fiber and magnetic bearings. Despite the brilliance, Brennan's monorail ultimately failed to catch on commercially. And the reason is pretty simple. Lugging around heavy steel flywheels spinning at 3,000 RPM was incredibly dangerous and incredibly expensive. If one of those steel flywheels shattered, you're dealing with deadly shrapnel. But modern engineering has completely changed the math on this. Today, we replace that heavy steel with ultra-strong, lightweight carbon fiber composites. Because carbon fiber is vastly stronger under centrifugal stress and, crucially, safely disintegrates into harmless dust if it ever fails, these modern gyros can spin at mind-boggling speeds. We're talking upwards of 50,000 RPM inside a sealed vacuum. It's a total game changer. But hold on, how do you spin something at 50,000 RPM without the mechanical bearings just instantly melting from the sheer friction? Simple. You remove the physical contact completely. Engineers use active magnetic bearings, or AMBs. First, high-resolution sensors monitor the rotor's exact position at a micro level of precision, literally thousands of times a second. Then, a digital processor instantly calculates the necessary adjustments. Finally, electromagnets dynamically levitate the spinning rotor mid-air, leaving a gap of just 0.15 millimeters. The result? Zero friction and zero wear. No way, right? That brings us to section 3, the hybrid transit ecosystem. Think about traditional dual-rail trains for a second. They're incredibly heavy and usually limited to just 4 to 6% inclines. But look at the alternatives we have now.
Cable-suspended systems like the Aerobus can span massive 600-meter canyons without needing a single concrete pillar. Cable liners handle 10% mountain grades effortlessly, and gyro-stabilized single rails, well, because they are so lightweight, they can take on astonishing 15% grades without losing traction. What we're looking at is a future where modular cabins can just seamlessly transition back and forth between city single rails and mountain cable networks.
And hey, this isn't just some wild theory on a drawing board. The Monocab Owl project over in Germany is actively reviving abandoned rural single-track railway lines today. They're using these self-balancing, autonomous battery-electric cabins that carry 4 to 6 passengers. Because they balance on just one rail of a standard track using those active control moment gyroscopes, 2 monocabs can actually safely pass each other traveling in opposite directions on the exact same single-track line. Talk about radically expanding the capacity of existing infrastructure. It's pretty much like having your own personal on-demand pod. All right, shifting gears to Section 4, Deep Earth Geothermal Power.
So how exactly do we pivot from moving people to moving energy using the exact same physics? Let's talk about unlocking what might be the ultimate clean baseload power source. Historically, geothermal energy has been limited to places with natural hot springs, places like Iceland. But consider this number, 70%. By borrowing horizontal drilling techniques right out of the oil and gas industry, a company called Fervo Energy has managed to slash drilling times by a staggering 70%. This massive drop in costs completely transforms the economics of geothermal energy, making it viable almost anywhere on the map. Let's break down how this essentially creates a massive underground radiator. Fervo builds what's known as an enhanced geothermal system, or EGS. First, they drill horizontally into hot, dry rock, and then they induce tiny connecting fractures. Next, they drill a second parallel well to intercept those exact fractures. It's kind of like building an underground ladder, where the 2 wells are the vertical rails and the rock fractures are the horizontal rungs. So they pump cold water down one side, it slowly absorbs the Earth's immense heat as it travels through those rungs, and then it comes up the other side as superheated fluid. And that fluid is used to drive power turbines 24/7. And the results are honestly spectacular. Fervo's Project Red out in Nevada operated continuously for over 600 days. Impressively, it achieved a 20% thermal recovery factor within just 2 years. That far exceeds Department of Energy benchmarks. Pulling this much stable baseload heat out of the ground absolutely proved that this underground ladder doesn't just quickly cool down, it works reliably at a commercial scale. It's a genuine game changer for the power grid. Finally, let's look at Section 5, drilling with gyrotron beams. Here's the catch, though. To power the entire globe, we really need to go deeper, down to super hot, supercritical rock. And this brings us to the fundamental depth problem. If you want to drill 10 to 20 kilometers down to tap into infinite 500 degrees Celsius heat, traditional rotary drilling completely fails. At those immense pressures and temperatures, conventional mechanical drill bits are literally pulverized instantly. They just melt. And replacing a melted bit isn't just an annoyance. You have to pull miles of heavy pipe out of the ground inch by inch. It takes days and it costs millions of dollars. Well, the mind-blowing solution to this comes from a startup called Quaise Energy, and it relies on a device called the gyrotron. A gyrotron uses rotational physics, specifically spinning electrons in a magnetic field, to generate high-power millimeter waves. Originally developed for nuclear fusion research, this directed energy beam is sent straight down the borehole, and it just effortlessly vaporizes the ultra-hard bedrock. Even better, it actually melts the edge of the hole into a solid vitrified glass liner as it goes. That means you don't even need to install steel casings. Quaise is actually planning to deploy these at old coal plants so they can swap out dirty boilers for infinite super hot geothermal steam. How cool is that? And that brings us to the end of today's explainer. When you trace the line from Louis Brennan's gravity-defying monorail cars back in 1910 to modern levitating carbon fiber flywheels, and now to gyrotron beams spinning electrons to vaporize rock miles beneath our feet, well, it leaves us with a pretty big question. Could the humble spinning physics of the gyroscope, an idea imagined well over a century ago, truly be the key to unlocking our entire clean energy and transit future? Something to think about. Thanks so much for joining me, and keep asking those big questions.